Section 13.3 is about dilations. So we're going to start out with just a basic definition of what a dilation is. A dilation, also sometimes called a size transformation or a scaling, is a transformation in which angles stay the same and lengths are adjusted by a fixed ratio. Now, a size transformation is not an isometry. Do you remember what an isometry was? The length stays the same. It preserves distances. No sizes change. All that language that we encountered back in 13.1. So this is not an isometry. The pre-image and the image are similar, but they are not congruent. So the most obvious dilation in the room right now is my iPad screen and the projected image on the board, right? All the ratios stay the same, and it just enlarges it. So a dilation might enlarge. It might also make it smaller. So it could shrink it up, okay? So there's not a specific one way or another. So you have to be really careful when you're looking at the information, whether or not the dilation is going from small to big or big to small. So just be careful when you're looking at the questions that are being asked. A dilation must have a center around which the scaling happens and a scale factor. That scale factor has to be positive. It's not 1. If it were equal to 1, then it would be the exact same size. If it's between 0 and 1, it would shrink it. Do you guys know what shrink eatings are? Okay, most of you nodded your head. That's good. I didn't know if those still actually existed. They were in my childhood. So, yeah, shrink eating. So think about the shrinky drinks, right? They shrink up, but it's the same image that you started with. Or if the number's bigger than 1, that's when it enlarges it. Okay? Now, we've encountered this before. We called them similar shapes, similar polygons, similar triangles. You still have one on your test that you're working with right now about similar triangles, right? And you had to identify which angle with which angle and stuff like that, right? But the ratio thing, which is my point to be bringing up right now, was the same. If the ratio was bigger than 1, it made the second, the image, bigger. And if the ratio was smaller, like less than 1, it made it smaller, okay? So we're going to talk about a specific transformation. This says to describe the transformation of triangle ABC into triangle A prime, B prime, C prime. Now notice over here, in order to describe it, you have to describe 2 facts about it. You have to talk about the scale factor. That's the one people usually remember to talk about. But you actually also have to talk about the center of the dilation. Where is it expanding from? So like on my screen right now, when we're talking about the expansion here, it's expanding around the very center of my screen. Otherwise, on this particular one, my images would be distorted, okay? So take a look at this one. And I want to show you that the size, or the dilation center, does not have to actually be on the object. I thought I got the pink there. Hang on, let me try again. This dot right down here in the left-hand corner is the center of my transformation. Okay? And here's how I know that it's not on the object itself. Do you see how the black triangle looks almost like it's also been shifted into the blue triangle? That kind of a shift look, or that look where it looks like it's been shifted, only happens when that dilation center is not on the object. Think about what would happen if it were on the object. So I'm going to draw a little picture over here on the side. If I had this triangle, don't look too closely to this, too much detail here. But if I were dilating around the corner point down here, what would happen, and let's say I just doubled it. I just doubled the length and widths of things, okay? So if I did that, what would happen is that this part right there would stay the same, and the side lengths would simply get twice as long. So it would look like that, and then I'd connect my endpoints. Well, it connected them, pretend. Okay? So when I'm dilating around an object, a point that's on the object, then that point stays stationary. But over in our image, the point doesn't stay stationary. It actually starts right here at C, and it moves, or sort of looks like it moves, to C prime. Okay? So the dilation center on this one can't be on the object because the object's vertices all moved. So the center, and that's why they're drawing it the way they did with the, down here, with the object. That is a terrible color to have used. Let me try that again. That one will work. That's why they're actually drawing the object center in. So that's your clue, right? The clue is that they've actually drawn something else in. So on this one, the center of dilation is at, do they give it a name? We'll just call it the origin. We'll just say it's at 0, 0. And we'll count from there, okay? So if our center of our dilation is down here at 0, 0, you could call it O if you wanted to for origin or something like that. That'd be fine. Then the other thing we have to do is we have to identify the scale factor. Now, the scale factor talks about how much bigger or smaller, however you think about it, the object becomes. So this was the original side length. How long is it? 3. This is our new side length. How long is it? It's 6. So what's the scale factor?
2.
It's 2. Do you guys see that okay? It's double the size, at least length and width wise, okay? So it is a scale, center at 0, 0 or at the origin or however we, the bottom left-hand corner, however you want to describe it. It's that dot. And it has a scale factor of 2. All the side lengths doubled. Now let's do a few more facts about dilations. For any dilation with center O and scale factor bigger than 0, the following are true. So these are just true facts. The image of a line segment is a line segment parallel to the original line segment and r times as long. The image of an angle is an angle congruent to the original angle. We say that two figures are similar if it is possible to transform one into the other by a sequence of isometries followed by a dilation. So we're going to flip back to that last screen for a moment to talk about the first couple of these. Well, actually all of them. The first fact that's sort of bulleted on here is that the image of a line segment is a line segment parallel to the original line segment and r times as long. So notice the red line segments that I've listed. They're parallel, right? Yeah, they're parallel. And the second one that I drew in, the bigger triangle one, was twice as long as the first one. That's all that that first fact is saying. The second fact is saying that all of the angle measures were preserved. So sure enough, oops, sorry about that. Sure enough, all of those angles are the same as what they started with. The easiest one, of course, to verify that with would be this corner, right? Those are still 90 degrees. But you could verify it very much the same way as this one. Do you see how this is forming this is a 45-degree angle because it's splitting the box in half, and you're getting that same image down here. And this happens to be 45 then as well up here, and you're getting that same 45 image up here, okay? So all those facts are true. Now, it is possible to say that the dilation on this one happened from that center O. You also could actually say that you could shift it, right? That's an isometry. I could move it, what would it be? Up to and right 1. If I moved the little triangle up to and right 1, then the C and the C prime would be in the same spot. Agreed? I could say that I've got a translation. That's what that's called, a translation, followed by a dilation, which dilated around the point C, the new location of C. That'd be another way to describe what's going on in this particular transformation. We did this once before in section, I think it was 13.2, it may have been 13.1, where we said, how is it a flip? Is it a rotation? Is it what? And we were like, okay, or a what else do we have? Reflection and shift and stuff. And we were like, sometimes there's more than one legitimate option, right? So that's going to happen here as well. All right, so let's take a look at example number 2. This says to find the image of triangle ABC under a dilation with center O and scale factor 1/2. So what can you tell me for sure, because center O is not on the object? It's going to look like everything shifted, right? None of the points that are already there, A, B, and C, are going to stay put. If the center were at A, B, or C, they would stay put, but it isn't. So all of those vertices are not going to coincide, or I should say none of those vertices are going to coincide when I'm done. What does it mean then to have a scale factor of 1/2? It means it's shrinking. Very good. So this image is going to be smaller than it was before because the scale factor is between 0 and 1. Okay? And because the O is in the middle of the object, so to speak, like it's in the interior of it, it's going to shrink toward that point, right? So when we do that, it's going to end up looking something like this. Sorry, that was terrible drawing. I don't know what my problem is. But you have the right idea. I should have used the line tool. Sorry about that. Everything seems to be half as long. In fact, you can take a look, right? This piece looks like it's the same length as that one, right? And yet the whole side AC was double that. We could do the same thing with the side over here, AB. This length is the same length as this piece right here. And you can see how they're crossing through the dots to do that. It's really, grid paper is very nice to be able to see that with. And again, it's double the length over there. And we could do the same thing with side BC. Any questions on that one? All right, so this is a good example of one where your description and mine might not match. So what I'd like for you to do is to do this problem on your own, and then I'd like you to compare it with somebody nearby you. Maybe your descriptions are going to be the same, and maybe they're not. If they're not the same, then I need you to talk together and see if you're both right, okay? So this says to describe a sequence of isometries followed by a dilation so that the larger triangle, on my screen it's the blue one, is the final image of the smaller triangle. Okay, so we're starting with the little triangle and we're going to end with the big triangle. So I would like for you to write down a series of transformations followed by dilations, whatever it takes, to get from the little triangle to the big triangle. And take a couple of minutes to do that and then compare with a neighbor. Okay, so somebody give me what you had as your steps to making this transformation happen. What did you have as step 1?
Is it okay if we
Yes, absolutely. In fact, you need to label it something, and otherwise we're not going to be able to talk about it, right? So, Eliana, which point did you label? Show us. Okay. So you labeled this point right here. What letter did you give it, just for fun?
I just put a coordinate 0, 0.
Okay. So you can put 0, 0. You could also, I heard over here, I think Alicia said A. I think I put O on my paper. So whatever you want to call it, give it a name. I think that's a good place to start. Did anybody choose a different point? Not today on where they started? Okay. There are sometimes very natural ways to choose it. Evidently, this must be one of those. And sometimes there's lots of good options, and people will choose different things. I know when I have done this particular test in the past, it's very interesting because when people start doing redos and stuff, they start comparing answers, and it becomes very confusing because you didn't start at the same spot. You didn't think about it the same way, and sometimes it's actually not as helpful to talk with somebody as it would be maybe to come and just start with what you started with. All right, so what did you do after you labeled that point A? Eliana, do you mind talking through what you did?
Okay. I rotated the smaller triangle 90 degrees counterclockwise.
Okay, that's not going to have enough space. Then what?
And then I gave it a scale factor of 2.
Okay, so you gave it a scale factor of 2, but when you have a scale factor of 2, you still have to have a center. So what was your center?
0.
This is still the point, same point that you had before. Scale factor of 2 with center. I called mine A on the screen, so I'll put A.
Can we call that an origin?
You could? Yeah, you just need to make sure that it's labeled on your picture, however you're describing it in your work. And as long as they match, we're good. Did anybody do this differently? No?
Not original, because I'm seeing.
You see it? What other way do you see, Rachel?
You could do the rotation around the point directly above A on the smaller triangle.
Okay, I'm going to give it another name. How about we call it B? Because we're that creative today. Okay, so what do you want to do around B?
It'd still be a 90-degree counterclockwise turn.
Okay, so that would actually end up putting the triangle right here when you were done. Is that right? Okay.
And then you'd have to shift it like x minus 3, y minus 2.
Okay, so you'd have to shift it up 1, right? And you'd have to shift it left 2. And that would move it to here. Agreed?
Yeah.
We could do a shift. And then,
And the scale factor 2, but the center would be.
yeah, oh, I'm sorry, I made my thing bigger when I did that. Sorry, it was right there. Yeah, scale factor of 2, but then the center would actually change on that if you did that, wouldn't it? Yeah, and that's actually why I was mentioning, so this would be our new point. Maybe we'll call it C because we're fun like that. Yeah, so when we shift it and we actually do the dilation is around a different point on that particular sort of set of isometries, right? So it does matter that, I didn't write it in up there. My bad. I'll fix that. Rotate 90 degrees counterclockwise. Should say around A. It does matter that even though we've identified the A here, that we identify the A here again, because it doesn't have to be the same point. Yeah. Okay, so some of you are probably like, yeah, but why would you do it that way? That would take lots more moving things around. And it would. Sometimes there's equally quick ways of moving ones around, moving an object around that will give it to you the same number of steps too. So, all right, last example for today, number 4. It's got a few parts to it. It says, consider the square OBCD with the following vertices. So, you have a grid on your paper, right? So go ahead and draw an XY axis. You're only going to need quadrant 1, so don't draw in quadrants 2, 3, and 4. You just don't need them. And go ahead and put these 4 points on your axis. Here's my axis. And I'm going to plot the 4 points. Okay, and it says this is a square, so it's intending for me to connect my vertices. Does that make sense? So consider square OBCD with vertices listed there, and then we're ready for part A. Part A says, perform a size transformation by multiplying the x and y coordinates of each point by 2. So let's write them out. So my new point, O prime, was originally 0, 0. And if I multiply the 0 and the 0 by 2, I get 0, 0. Yeah, not very exciting. All right, what's the next one? B prime. B is originally 0, 2. And if I multiply each of those coordinates by 2, what do I get? 0, 4, you bet. C was 2, 2, and if I multiply each of those coordinates, C prime becomes 4, 4. And D was originally 2, 0. Multiplying each of those coordinates by 2, I get 4, 0. It says perform a size transformation by multiplying x and y coordinates of each point by 2. And then it says we're going to translate each point up 1. So if I'm supposed to translate each of these up 1, how is that going to affect the ordered pair? You add 1 to the y. So this first point becomes 0, 1, and the second point becomes 0, 5, and then the third point becomes 4, 5, and the last point becomes 4, 1. So is everybody good with the two transformations that we did? All right, what we're going to do next is we're going to actually plot those ordered pairs. We're going to plot where we are, okay? If you want to plot the in-between spot where we just doubled the size, you can do that too. I think that it might be visually a little bit easier to sort of talk about, so I'm going to plot mine. So this was our sort of in-between one where I'm doubling everything, this pink one that I'm drawing. And then I'm going to shift it all up. And I'll have a blue one when I'm done. So the blue one right there is my final answer. Now on part B, we're going to draw the picture differently. So if you have space, I hope you haven't used your whole grid. You can draw the grid again. But we're going to actually do the transformation backwards of what we just did. Part B, I don't know why it says A, but it should say B, says to perform a size transformation by translating first everything up 1, and then second, we're going to double the coordinates, okay? And we're going to find the graph of the result. So, O, again, we're going to do this in order. So we're going to add 1. So it originally was 0, 0, so now it's 0, 1. B was originally 0, 2, so now it's 0, 3. C was originally 2, 2, so now it's 2, 3. And D was originally 2, 0, so now it's 2, 1. And then we're going to do what we did on the last screen, and we're going to double each of the coordinates as our second step instead of our first step. So if I double each of my coordinates on O, what am I going to get? My new O prime that I've written here. 0, 2. How about if I double my coordinates on 0, 3? 0, 6. What if I double my coordinates on 2, 3? 4, 6. And if I double up my coordinates on D? 4, 2. All right. I think I can plot those on the same graph that I already have, so maybe you can too if I make my graph kind of overlap my words. Red. Red sounds good. All right, so I'm supposed to start now at 0, 2 and go up to 0, 6. Is that right? Yeah. Zero, 2, 0, 6, 4, 6, and 4, 2. That's more or less where I am, my red one. For clarity, I'll come over here and I'll call these all double primes. That's part 2. So this was my pink. This one was blue. And part B was the red one. Compare A and B. The graphs, the red graph and the blue graph. What do you notice? How are they the same? How are they different?
They're congruent, but the red one is
good. They're congruent shapes.
Translate out 2.
2 from each other or 2 from the original? What are you comparing?
It's not the. Wait.
It's the blue and the red. Those are the graphs we're comparing, blue and red.
Oh, okay. So translate out 1.
It is up 1, right? The difference is that one of them's shifted up just a little bit higher. So they're congruent shapes, but you can call it the red one or the second one. The second transformation is shifted up 1. From the first. Why did that happen? Why didn't they land in the same spot?
Order of operations.
Okay, so this is important to realize is that the order in which you do your transformations matters, right? They don't end up in the same spot all the time. They might. It depends on what you're dealing with, but they don't always. So why, in the course of the actual steps we did it not work? Why did I end up 1 higher when I switched the order than the original one? What actually caused that to happen? Can you see what it did? Where was the shift? How far did I shift things actually each time? I did a shift of 1. Both of them had a shift of 1, correct? But on the first one, I shifted after I did it, right? On the second one, I shifted first. So what happens to a shift of 1 if you double it after? It's a shift of 2. So if you're comparing the pictures, this is what you were doing, Casey, before, the pink one to the red one, right? It's actually a shift of 2. And the reason is because that shift of 1 and then doubles the shift. And that's why your order of operations matters, especially with dilations. It matters with where the center is. It matters with whether you do the shift before you do the dilation or if you do it in the other direction. The order of operations matters.